Okay, in this lecture we will talk about micro droplets. Micro droplets have important applications in microfluidics, where we talk about discrete droplets. Okay, and discrete droplets in microfluidics in microchannels have formed a new area of microfluidics called digital microfluidics, and it has applications in different areas, including dosage system, where we talk about drug delivery application. It has application in chemical analysis and in microreactors. Okay. So, these micro droplets, the principle that is used to generate these micro droplets can be divided into two categories. One is closed loop control system, and the other one is the open loop system. Okay. So, let us look at the micro dispenser. Okay. As you can see here, they are divided into two groups. One is closed loop control dispenser, where we dispense a known volume, droplets of specified size, and using a pump and valve mechanism, and we closely monitor what its size is actually is, and then we provide a feedback signal to the control to generate the desired size. Okay. So, that works on the principle of closed loop system. Then in open loop system, open loop dispenser, we have two categories again. We have droplet dispensers, which just dispenses droplet that could be in air in ambient condition. So, these are thermoneumatic, electrochemical, thermomechanic, electrostatic, and piezoelectric. Similarly, we have in channel dispensers. Okay. So, these in channel dispensers are used to generate droplets inside microchannels. Okay. So, these droplets will be generated at a relatively high pressure than the ambient. Okay. So, here you can see there are different principles that are available. It could be pneumatic, thermoneumatic, or electrokinetic. Okay. So, having talked about that, let us look at kinetics of a micro droplet. Okay. Kinetics of micro droplet. So, one characteristics of micro droplets is that the total stored energy in the micro droplets is small. Okay. So, since the total stored energy is less, the droplets are clean, meaning the droplets do not have a tendency to get splashed or get broken. Okay. So, the micro droplets have small stored energy. So, they are called clean droplets. Okay. So, the total energy of a droplet can be divided into two components. One is because of the surface, which is called surface energy, and the other one is because of its movement, the kinetic energy. Okay. So, the total energy of a droplet can be divided into two parts. So, E will have a component Es plus Ek. Okay. So, this is the surface energy, and this is the kinetic energy. Okay. Now, the surface energy can be written as, so the surface energy can be written as Es is the area pi d0 square into the surface tension coefficient into sigma. So, this is the droplet diameter and this is the surface tension. Okay. Similarly, the kinetic energy Ek is half m u square, which is half pi d0 cube, that is the volume into density, the mass into u square. Okay. So, u is the velocity and rho is the density. Now, if you take a ratio of surface energy to kinetic energy, so here we see that the surface energy scales as d0 square and the kinetic energy scales as d0 cube. Okay. So, this scales as the surface area and kinetic energy scales as the volume, right. So, the ratio of the surface energy to kinetic energy is 1 over d0. Okay. So, what we see here is the ratio of the surface energy to kinetic energy will increase with miniaturization. As the size of the droplet will go down, the surface energy will become more and more dominant as compared to the kinetic energy. Okay. So, this ratio would increase, so it increases with miniaturization. Okay. So, the micro droplets which have large surface to surface energy to kinetic energy are clean, okay. And that is because there is not enough kinetic energy exist to form new surface. Okay. So, that is the reason why splasting and formation of new surfaces are avoided. Okay. So, the micro droplets have negligible kinetic energy, they have strong surface energy. So, splasting, for example, formation of tiny secondary droplets, smaller droplets around the main droplets, or the breakup of the droplets into different droplets are avoided, okay, because of the less kinetic energy of micro droplets. Okay. So, now if you take a ratio of kinetic energy to surface energy, if you do take a ratio of kinetic energy to surface energy, then it will be 1 over 12 into rho u square into characteristic length divided by the surface tension. Okay. And this term here is known as Weber number. Okay. So, we can write this is the characteristic length which could be the droplet dia, and this is surface tension. Okay. So, this is Weber number. So, you can write E k over E s as 1 over 12 into Weber number. Okay. So, what we see here is the Weber number is proportional to the droplet size. Okay. So, Weber number is proportional to the droplet size, and at micro scale since we are talking about micro droplets, the Weber number is small. Okay. The Weber number is small for micro droplets. Okay. So, with that information, let us move on and talk about a vertical injection of a droplet. Okay. So, we take a nozzle where the droplets are being injected in the vertical direction, and you want to study how the dynamics of this droplet evolves, okay, with time and space. Okay. So, we consider dynamics of droplets. And here we have vertical injection. Okay. So, this is the situation what we see here. This is a droplet which is being injected from the origin x equal to 0, y equal to 0 in the vertical direction. Okay. So, let us say this droplet is going towards the positive g direction or negative y direction. Okay. So, the different forces that are acting on the droplet, one is the gravitational force which is acting towards negative y, that is mg, and there is inertia force because the droplet is trying to accelerate. So, it is m dv into dt, and the drag force is trying to oppose the motion, okay, in the positive y direction, right. So, we talk about the force balance. Okay. So, these dynamics of droplets have in vertical injection have importance in design of dispensing system, okay, design of dispensing systems. So, one such example is shown here. Now, if you consider the force balance, then we have different forces here. One is the gravitational force, then the second one is the drag force, and the third one is the inertia force. Okay. So, the summation of all the forces is going to be 0. So, we can write, so this is different forces, we can mark it. This is gravitational force, this is drag force, and this is inertia force. Okay. Now, we can write down the expression for different forces. First, to write for inertia, this m into dv over dt, mass into acceleration. Drag force is opposing the inertia. So, this will be minus 3 pi eta a into the diameter of the droplet. Eta is the viscosity of air, let us say the droplet is being dispensed in open air, and then the gravitational force is mg equal to 0. Okay. So, this is the equation we have. Now, what are the boundary conditions? Now, at the initial velocity, at the nozzle, okay. So, the V0 is going to be minus V0, okay, and the terminal velocity. So, this is the initial velocity, the terminal velocity, this is negative because it is going in the negative y direction. So, that is why the vertical velocity at time t equal to 0 is minus V0. Now, the terminal velocity, that is V infinity. So, time tends to infinity, V infinity is going to be minus V infinity because in the negative y direction, and that can be found if we, when it reaches the terminal velocity, the acceleration will be 0, right. So, if the acceleration is 0, we can find what is the expression for V infinity by equating the drag and gravity. So, if you do that, we can find an expression for minus V infinity, which will be minus mg divided by 3 pi eta d 0, okay. And if you put in density to express mass, so we can minus rho g d 0 square divided by 18 eta a. So, that is going to be the terminal velocity. So, the terminal velocity can be found at the inertia force is 0, okay. Now, with these two conditions we can solve this equation, to predict what is going to be the expression for the velocity. So, the solution for the velocity will be V as a function of t is going to be minus V infinity minus V 0 minus V infinity exponential minus t divided by rho d 0 square divided by 18 eta a, okay. Now, this term is the time constant, okay. So, this is the time constant. So, we can write the time constant tau equal to rho d 0 square divided by 18 eta a. So, this time constant is the time constant for acceleration and deceleration, okay. So, time constant for acceleration and deceleration, okay. Now, you can observe here what is interesting is that both the time constant as well as the terminal velocity, they are independent of the initial velocity, okay. That is an interesting observation. Now, with that we can find the flying distance, how much distance a droplet can fly. The flying distance can be found. So, y equal to, if you integrate from 0 to t, v as a function of t into dt, okay. So, if you do that, we can get an expression which looks like this. So, minus v infinity t plus v 0 minus v infinity tau into exponential minus t over tau minus 1, okay. So, that is the expression for the flying distance. So, this is how much the droplet can fly at a particular time, okay. So, now let us look at some plots related to what we have just found in terms of the velocity and the flying distance. So, what we can see here, the velocity v, okay, the vertical velocity v t is plotted with time for different droplet diameters, okay, 50 micron, 30 micron and 10 micron, and we see that the smaller the droplet, slower is the terminal velocity, okay. So, this is, you can see this is negative because it is in the negative y direction and is increasing in this direction, velocity is increasing in this direction. So, you can see that for a 10 micron droplet, the terminal velocity is going to be less as compared to that for a 50 micron droplet. Okay. And what we also observe is that here this is the flying distance versus time. So, what you can see here is that the flying distance for a larger droplet is going to be large. Okay. So, this is about for a for a 50 micron droplet, the flying distance is about 400 micron, sorry 10 millimeter. Okay. As you can see here. So, this is around 10 millimeter. So, this is actually around 10 millimeter, and for a 10 micron droplet the distance is about 400 micron. Okay. So, the flying distance for a larger droplet is going to be higher than that in case of a smaller droplet. Similarly, if you look at the terminal velocity, irrespective of the droplet size, the terminal velocities are going to be the same. Okay. So, the terminal velocities are independent of the droplet size, as you can see from here. And here you see droplets having different initial velocity. Okay. V0 1 meter per second to V0 3 meter per second, 1, 2 and 3 meter per second. And what you can see is similarly the terminal velocity is independent of the initial velocity of the droplet. Okay. So, that is an important conclusion to make, right. And as you can see here, what this plot means is that the the smaller droplet can achieve the terminal velocity in a lower flying distance. Okay. So, what it means is that a smaller droplet attains terminal velocity at a smaller flying distance. Okay. And here we see that the terminal velocity is independent of the initial velocity, okay, but the terminal velocity is dependent on the diameter. Okay. As you can see here, both time constant and the terminal velocities, they are dependent on the droplet diameter, but they are independent of the initial velocity of the droplet. Okay. So, the time constant and terminal velocities are independent of the initial droplet velocity. So, that is what you see here. So, irrespective of the initial velocity, the terminal velocities are the same. Okay. So, terminal velocity independent of initial droplet velocity. Okay. And here we see that droplets of different initial velocities, they would reach the terminal velocity around same time. Okay. As you can see here, so their terminal velocities are reached around the same time. Okay. So, here we say that the droplet with different initial velocity reach terminal velocity at same time. Okay. However, the initial velocity affects the flying distance. Okay. Here you can see the flying distance for a larger velocity is going to be higher as compared to the smaller initial velocity. So, initial velocity affects the flying distance. Okay. The initial velocity affects the flying distance. So, with that let us consider droplet injected horizontally. Okay. So, we talk about the droplet dynamics in case of horizontal injection. Okay. So, here you can see this droplet initially at x equal to 0, y equal to 0 is being injected horizontally, and at any instant this will be the force distribution. There will be inertia force along x direction and inertia force along y direction, and the gravitational force acting in the y direction, and then drag force acting in the negative x direction. Okay. So, we can write the force balance. Okay. So, along x axis, in the x axis we can write that the inertia force plus the drag force is going to be 0, and y axis the inertia force, drag force plus gravitational force are going to be 0. Okay. So, we can write down, expand the expressions. In x axis we can write m du over dt minus 3 pi d0 eta u is going to be 0. So, this actually plus and this is minus because it is in negative x direction, and so this is the first equation. The second equation is m dv over dt, that is the inertia, minus 3 pi eta d0 v plus mg is going to be 0, right. So, we want to solve these two equations. What are the boundary conditions? The boundary conditions are u at equal to 0 is going to be 0 and u at infinity is going to be, sorry, the v at infinity is going to be minus v infinity. Okay. So, that is going to the final terminal velocity, because even if the droplet is injected horizontally, finally it is going to fall vertically because it is being released into air. So, that is the terminal velocity, but initially it has x velocity u0. So, with that we can solve for ut is going to be u0 into exponential minus t over tau, and vt is going to be minus v infinity 1 minus exponential minus t over tau. Okay. So, these are the two expressions for the x and y velocities, and here the time constant tau is going to be rho d0 square over 18 eta a. Okay. And if you integrate this velocity with time, okay, if you integrate over time, then you can get an expression for the flying distance. Okay. So, the flying distances you can get an expression for that. So, xt is going to be u0 tau into 1 minus exponential minus t over tau, and yt is going to be minus v infinity into t minus tau exponential minus t over tau. Okay. So, those are the expression for the flying distance. Okay. Now if you look at a plot showing the velocities and flying distance with time, this is what is shown here. Here we are showing kinetic energy versus time, and so you can see that the final kinetic energy is going to depend on the droplet size. Okay. So this is the droplet 50 micron, 30 micron and 10 micron. So you can see that the kinetic energy of a larger droplet is much higher as compared to that of a smaller droplet. Okay. And here you can see the x distance with y distance. Okay. And here you can see that the small droplets cannot keep long horizontal trajectory. Okay. The small droplets fall off very quickly, okay, following this trend, whereas the larger droplets can take a longer horizontal trajectory. Okay. So that is what we have seen here, and that is also here we plot x distance and y distance with different initial velocities, 1 meter per second, 2 meter per second and 3 meter per second. So this is actually the horizontal velocity u, and we can see that for a droplet that is being injected at a larger initial velocity can go a larger horizontal distance. Okay. That is what we have seen. This is for 1 meter per second and this is for 3 meter per second. Okay. So with that discussion, let us look at an example problem. So here we are talking about a water droplet of diameter 50 micron moving in air, and that breaks into two identical droplets. Okay. So we have initially one big droplet of some diameter d0, and that breaks into two identical droplets, okay, droplet 1 and 2. So the surface tension of water is given 72 × 10⁻³ the initial droplet size is given 50 micron, the density is given 1000 kg per meter cube. So it is a water droplet, and we are neglecting energy loss due to friction. We want to find out the minimum speed of the droplet required for the breakup to occur. Okay. Now to solve that, we can we are saying that this droplet is going to break into two identical droplets. Okay. So their sizes are going to be the same. Okay. Let us say the droplet size here is d nu. Okay. So now first consider the initial size of the droplet, total volume of the droplet is going to be sum of the volumes of the two individual droplets after breakup. Okay. So the total volume 4/3 into pi d nu cube 2 into that will be equal to 4/3, sorry, we are using pi d cube by 6 because it is the droplet that we are using, diameter that we are using, into pi d0 cube over 6. Okay. So what we find here is the diameter of the new droplet is going to be d0 divided by 2 to the power 1/3. Okay. Now to make the droplet breakup to happen, the kinetic energy has to exceed the surface energy. Okay. So for breakup to occur, so this is mass conservation. So now breakup to occur, the surface the kinetic energy has to be greater than the surface energy. Okay. So the kinetic energy you can write 1/12 pi rho d0 cube u square has to be greater than 2 pi d nu square into rho. So, the kinetic energy of the droplet before breakup has to be greater than the surface energy of the two offspring droplets. Okay. So, under that condition, so this is the surface energy after breakup, okay, total surface energy, and this is the initial kinetic energy. So, with this we can substitute in terms of d0. So, this should be greater than 2 pi d0 square divided by d 2 to the power 2 by 3 into rho, okay, into sigma. Right. So, you can find the minimum velocity u has to be greater than equal to 24 sigma divided by 2 to the power 2 by 3 rho d0 square root, okay. So, that should be greater than 3.89 sigma divided by rho d0, and now if you substitute the values, sigma is so is 3.89 into sigma is 7 into 10 to the power minus 3 divided by 1000 into 50 into 10 to the power minus 3 square root. So, it should be greater than 4.67 meter per second, okay. So, the droplet velocity has to be minimum 4.67 meter per second, so that the droplet can break into two identical droplets, okay. So, with that let us move on and talk about generation droplets in channels, okay. So, here we talk about droplet formation in channels. In microchannels, okay. As you can see here, there are two mechanisms available to generate droplets in microchannel. One is the pinching mechanism, where you have the discrete phase in a center channel, and this discrete phase is pinched by a continuous phase, so that the dispersed phase forms a jetting structure, and initially the surface tension will be very high, and as the droplet size grow with time, the drag force exceeds the surface tension force. So, there is droplet formation, and similar effect can be realized in case of the second type of droplet generator is based on the shearing mechanism, okay. So, basically we would have two different types of mechanisms. In one we would have the discrete phase at the center, and this will be pinched by two continuous phases. So, this is the discrete phase, this is continuous phase, this is also continuous. So, the discrete phase will form a jet sort of structure. So, initially the surface tension will be very high, okay, and as the size of the droplet would increase, the drag force will increase, and finally the droplets will be released, okay. So, that is known as pinched structure, and the second kind of structure is shown here, which is the shear structure. So, here again the discrete phase is coming as a liquid from the top here, this is the discrete flow rate, this is the continuous phase, and this there is a jetting formation around here, and as the drag force increases, as the droplet size increases, the drag force would increase, and finally because of the instability at the interface the liquid is going to separate from the liquid source into discrete droplets, okay, which are carried downstream. Now if you look at so what we see is that the droplet formation occurs due to instability, okay, and the condition is that the discrete and continuous phases are immiscible, they should not mix with each other, okay. So in that case you can generate droplets and the size and the behavior of the droplets are governed by two parameters, one is the capillary number and the second one is the ratio of the discrete phase to the total flow rate of the continuous plus discrete, okay. So there are two parameters that govern the size and behavior are controlled by, one is the capillary number and the second one is the fraction of sample flow. Okay. The capillary number Ca is defined as U into eta over surface tension, okay. So that is the definition of capillary number. The fraction of sample flow, this is Ca, this is R is defined as Q sample, so that is the discrete phase divided by Q sample plus the continuous phase, or it is also known as the carrier phase, okay. So with that definition let us look at the phase diagram. So as you can see here we can identify three different regimes, one Plog regime, the second one is the transition regime and the third one is the laminar regime, okay. The Plog regime is the regime in which the capillary number is low, okay. So here the capillary number is low. So what happens is that the droplets start to break right at the junction, the droplet break here and relatively larger droplets are generated in the Plog regime, okay. Now as the capillary number increase, okay, so as the capillary number increase the droplets are going to be reduced in size, okay. So the droplet size is going to be reduced and instead of breaking right at the junction the breakup occurs slightly downstream, okay. So that is known as transition regime, and then we would have the laminar regime where the breakup occurs far away from the junction. So the sample and the carrier fluid, the discrete and the continuous phase flow side by side till some distance and then the breakup would start to occur, and that is known as the laminar regime, okay. So we identified three different regimes. So this is the continuous phase or the carrier fluid, this is the discrete phase or the sample flow rate, okay. So we identified three different regimes. One is the Plog regime, the Plog regime, so here the capillary number is small, okay, and the droplets break at the junction, okay. Then the second regime is the transition regime. So, here the capillary number is increased and the breakup occurs slightly downstream. Okay. And the third regime is the laminar regime, and here the side by side flow occurs. So, two phases will flow side by side occurs, and the capillary number is large. Okay. So, now let us look at the force balance on the droplets. So, let us consider here. So, we have discrete fluid coming in through this at a flow rate q d, the continuous phase comes in at q c. So, the droplet try to break. Now, here we try to do a force balance. So, one is the drag force that is going to be balanced by, that is going to overcome the surface tension to to enable the breakup. Okay. So, we take a force balance, we make some assumption first. So, we make some assumption that small droplet size, so that alpha, which is the ratio between q d over q c, is going to be less than 1. We assume steady state and no inertia and buoyancy. So, under those assumptions, if you write down the force balance, so the drag force is going to be equal to the surface tension force. So, you can write half C d into rho u c square into A d is going to be C s pi d I into rho. So, this is drag coefficient, this is density, and this is the average carrier velocity, carrier fluid velocity, and this is the effective drag area, effective drag surface area. This is the surface tension coefficient, surface tension. So, we can write the expression for the effective drag area, which is pi into d d square divided by 2. Okay. So, this is the channel size, okay. This is the droplet size. Now, we can substitute this in this equation. If you do that, we will get half into C d into rho u c square into pi d d square divided by 2 will be C s pi d I into rho. So, you can find an expression for d d, diameter of the droplet, equal to 2 C s over C d into d I into rho divided by rho c u c square root. Okay. Now, we can find out the droplet formation frequency, the droplet formation frequency, which is known as F will be q d, the flow rate of the discrete phase divided by the velocity of the discrete phase, and you can write this as, if you use expression for d d and use q d equal to alpha q c, then you can write the expression for the frequency. F will be 3 alpha d c square divided by 16 into Cs over Cd into di to the power 3 by 2 into rho c to the power 3 by 2 Uc to the power 4 divided by rho to the power 3 by 2. Okay. So, you can find out the expression for the frequency, how frequently the droplets are going to be generated. Okay. And here dc is the dia of carrier channel. Okay. So, we have seen for droplet generation along a channel, knowing the droplet geometry and the parameters, the flow rates and the fluidic parameter of the continuous and discrete phase, we can find out what is going to be the diameter of the droplet and at what frequency these droplets are going to be generated. Okay. So, with that let us stop here.